Hello and welcome back to Aerospace and Mechanical Lab 1. Today we're going to talk about tensile test, which is going to be your lab after you come back from spring break. So tensile test, to understand the tensile test a little bit better, we have to discuss the basics of stress and strain, and then we have to talk about deformation and different types of failure. We will talk about the stress-strain care for metals, and a stress-strain care for composites, and eventually we will go to lab 7. Sorry about the numbering. Lab 7, we will talk about the tensile test. Okay, so we have different types of external loading. One is a tensile, which is essentially when you pull two sides of, or just one side of, one beam or one structure. We have compressive load, when you compress two sides or just one side of a beam. We have shear and we have torsion. We already have seen examples of shear force and torsion in our labs. Today we are going to discuss a tensile load, and later on in lab 10 in the manufacturing lab we will see how a compressive load works. But essentially our focus today is going to be on tensile load, and we're going to learn how to do a tensile test and what the purpose of a tensile test is. But to relate the load to the deformation, to the response of the material to any external load, we are going to use the Hooke's law that essentially tells us that there's a linear relationship between the load P and the change of length. And these two are essentially going to be equal to each other when you multiply your change of length, elongation, by the spring constant. So whatever we do here, and in general in the mechanics of material, in the elastic region, is going to be based on the Hooke's law for springs. Okay, so based on this Hooke's law, we can see that we can define a stress and a strain instead of load and elongation. Essentially, when you divide your elongation by the original length, initial length of the material, or any length, any base length, doesn't have to be the initial length, but we usually use the initial length for analysis. We can calculate the strain of the material, and we can define a stress as our load P divided by the cross-sectional area of the material. Just to make sure that we are all on the same page, look at this example A. The length that you want to use for your strain in the tensile test is going to be this length, but the cross-sectional area is this area. So this is the load that you are exerting. This is the cross-sectional area you are exerting your load on, and the length is the length in which direction the elongation actually happens. So we said based on the Hooke's law, the two should be linearly related, and the linear relationship is going to be presented like this. Sigma has to be equals to E, the modulus of elasticity, or Young's modulus, multiplied by a strain. But this is not always true, as you can see in these graphs, that these are experimental graphs for sigma and epsilon, and we actually have load and elongation here for these three material as well. As you can see, there is a linear region which we call the elastic region, and then after the material has yielded to the load, we enter the plastic region. The difference between these two is that in the plastic region, if you remove the load, your material is going to act exactly like a spring and go back to its original form, original shape. And so the elongation will vanish, right? But or deformation will vanish. But in the plastic region, there will be some going back, but it doesn't go back all the way to its original shape, original form. Which means that in the plastic region, there will be a permanent deformation, whereas in the elastic region, there won't be any permanent deformations. Okay, so this is a graph that you should give us in your lab report. You are going to apply a load And because of that load, there will be elongation, and you will see a linear region, very small linear region, and then the linear region will be followed by a plastic region, and then eventually you are going to see a rupture. There are a couple of things that you have to keep in mind, that we usually deal with engineering stress instead of true stress. Engineering instead of true stress. And what that means is that to calculate the stress, we divide the load to an initial value of the cross section. Because the idea is if you apply a tensile load to any of your sample, your cross section also changes with time with your load, right? But to make our lives easier, we don't want to go back and measure the cross section and again. We just use an engineering stress, which means that we divide the load by an initial cross-sectional area. But if you divide the load by the true area, by the real-time area, you will get something called the true stress. And that is not the goal of the slab if you want to use the, just the initial area to do our calculation. Okay, so we have talked about the elastic region, we have talked about the plastic region. We need to talk about the length of the plastic region first of all, and then how the rupture happens. We do have different types of metals, if you're only talking about metals or material in general. Our material can be very ductile, which essentially means that they are very soft metals, meaning that they will have a very large plastic region. It will take a long time for them to actually break. Then we have moderately ductile material, which will show a moderately ductile fracture or rupture, meaning that the plastic region is large, but it's not as large as it's not as big as a very ductile material. It's typical for metals. Metals are usually moderately ductile, and eventually we get to cold metals or ceramics, which show brittle fracture, meaning that there is little to no plastic region. So as soon as you enter the material yields, you will see the rupture and the breaking of the material. And this will be the top of fracture you're going to see for each type of material. For a very ductile material, you will see a complete necking. There is no breakage. It's just a complete necking, and then the material, I guess, separates. The two top parts of the material separates from each other. Moderately ductile, you will see a little bit of necking, and then there will be a breakage. Brittle material, there is no, in theory, we don't really have a real brittle material. In theory, there is no necking at all, and there is a very clean break. Okay. But when you move to composites, things are going to become a little different. Composite or anisotropic materials can show different characteristics in different directions. For example, the material that we see here, it's a glass epoxy with a unidirectional composite, meaning that the fibers are only placed in one direction. It shows a modulus of elasticity of 45 kilonewtons per millimeters squared in one direction. In the other direction, it will show only 8 kilonewtons per millimeter squared. So this composite is stronger than a lot of metals. This side of it is actually weaker than a lot of metal. For a carbon epoxy, it's the same scenario. For a unidirectional composite. Well, what's the difference between a unidirectional and multidirectional? Essentially, a unidirectional composite is where you have one direction in which the carbon fibers or glass fibers or whatever are placed, and then they are connected to each other using epoxy. So if you apply stress in this direction, they won't be able to resist against this stress, and the material easily breaks. But in this direction, the material is very strong. The material in this direction, the strength of the material is determined by the resin, which are usually very soft, don't really have a high modulus of elasticity. But a non-unidirectional material, something like this, so you might have fiber in all directions. Okay, anisotropic material, essentially different characteristics in different directions. So the type of fracture we're going to see in this type of material might be very different from the fracture we see in metals or uniform materials in general, right? One type of fracture that we might see is called delamination of the layers. These materials are usually made up of a lot of layers that are put on top of each other, and if you apply a level of stress, they might delaminate, meaning that these laminas will separate from each other before the actual breakage of the fiber. To avoid these delaminations, we can add 3D reinforcements, or we can have vertically allied carbon nanotubes. Essentially, we can make sure that this material is stronger in this direction as well, so that the delamination won't occur. So, different types of fractures. We can have a very ductile fracture, we can have moderately ductile fracture, brittle fracture, or we can have a different type of failure, which is a fracture by itself, very similar to a fracture, but it has a very different behavior due to the different nature of the composite material, called delamination. So in the lab, you will be given two different samples of aluminum 6061. One is annealed, one is hardened. So essentially one is softer, one is harder. And you will be given two different plastics and a composite material. For all of these, you have to run the tensile test. And we'll try to give at least each person one sample to do the test in the labs. And eventually you have to determine the modulus of elasticity for us. The software that we give you also determines the modulus of elasticity for you, but I want you to do the determination from the data you receive in the lab, for the data you receive for the load and the elongation in the lab. The elongation measurements will be done using an extensometer, and you will learn all of this when you watch the lab video. You have to keep in mind the lab right now is located in the basement of civil engineering site in room C004. We have plans to move this tensile test machine to our side of the building, but it hasn't materialized yet. So you might not have 5 different samples. You might be given only 4 samples, but the idea is for all of them you have to run a tensile test. You have to share your results with your section mates, with the other groups that are in your section, or you can share your results with other groups that are different sections. The idea is you have to have more than one measurement to do a statistical analysis and find the confidence interval for us. Thank you for listening. Enjoy the rest of your day.